theta motion. Nearest stop for theta motion will be rho del v theta by del t plus vr del v theta by del r plus v theta by r del v theta by del theta plus v phi upon r sin theta del v theta by del phi plus vr v theta minus v phi square cot theta upon r, that is equals to minus 1 by r del p by del theta plus mu 1 by r square del by del r square del v theta by del r plus 1 by r square del by del theta of 1 by sin theta del by del theta of v theta sin theta plus 1 by r square sin square theta del square v theta upon del phi square plus 2 by r square del vr by del theta minus 2 by r square cot theta by sin theta del v phi by del phi plus rho g theta. Now coming on to our phi equation of motion, that will be so our phi equation of motion will be rho del v phi by del t plus vr del v phi by del r plus v theta by r del v phi upon del theta plus v phi by r sin theta del v phi upon del phi plus v phi vr plus v theta v phi cot theta upon r equals to minus 1 by r sin theta del p by del phi plus mu 1 by r square del by del r of r square del v phi upon del r plus 1 by r square del by del theta 1 upon sin theta del by del theta of v phi sin theta plus 1 by r square sin square theta del square v phi upon del phi square plus 2 by r square sin theta del vr upon del phi plus 2 cot theta by r square sin theta del v theta by del phi plus rho g phi. So this will be our phi equation of motion. Now as our r equation gives, simplifying the terms, like in our r equation of motion, our problem is steady state, so this term is 0, coming vr is 0, so this term is 0, our v theta is 0, so this term is also 0, and vr is 0, so this term will be 0, and our v theta is 0, so this will be neglected, and v phi, some part of this term is there, del p by del r will be there, and our vr is 0, so this is 0, vr is 0, so this is again 0, and our vr is 0, so this is also 0, and in our r direction there is no gravitational force, and there will be actually centrifugal force, but we cannot consider it in rho gr. So after cancelling out all the terms, and we will be getting our r component equation as v phi square upon r equal to minus del p by del r. So this will be our r component of equation. Now again applying the same concept of cancelling out terms, our theta equation of motion is this. So again the problem is steady state, so this is 0, v theta is 0, our v theta is 0, our v theta is 0, vr v theta 0, this term will be there, and our v theta is 0, v theta is 0, v theta is 0, vr is 0, and this term will be there, and in our theta direction there will be no acceleration, and in theta direction there will be, in theta direction gravity will act. Like when theta equal to 0, the gravity will not be applicable, but when theta equal to 90 degree, the gravitational forces act vertically. So consider the effect of gravity along with the pressure. We'll be having our theta component of equation as, our theta component of equation will be minus v phi square cot theta by r equal to minus 1 by r del p by del theta. This will be our final theta component equation. Now again simplifying the phi component of equation, we'll be having by same method we'll be having phi component of equation as 0 equal to 1 by r square del by del r of r square v phi, r square del v phi by del r plus 1 by r square of del by del theta into 1 upon sin theta del by del theta of v phi sin theta. So this will be our phi component of equation after cancelling out the 0 terms. Now we are having 3 boundary condition, applying all those 3 boundary conditions in our equations. So we'll be getting we will be, as our VR and V theta is 0, so we will be not consider the r component as well as the theta component equation in our problem. We'll only dealing with the phi component problem. So because our v phi is also only the non-zero velocity, so let us assume our v phi is some function of r multiplied by sin theta. So without any assumption, solving that complex equation is a little tougher task for us. So we'll be assuming v phi is some function of r into sin of theta. Now as we put our v phi as this, so our equation reduces to, phi component equation reduces to as dy dr of r square df by dr minus 2f equal to 0. This equation satisfies this equation. Now after that, a very general solution of this equation is available, f equal to c1r plus c2 by r square. This is the solution of above equation. This solution satisfies this equation. Now after that, we'll be putting our boundary condition in our solution. So putting our first boundary condition as at r equal to capital R, Vr equal to 0, V theta equal to 0, and V phi equal to r omega sin theta. Since we have this solution of V phi, so our V phi will become c1r plus c2 by r square whole multiplied by sin theta. Now our boundary condition is at r equal to capital R, our V phi will be r omega sin theta. So this, putting our V phi as r omega sin theta, will be getting c1r plus c2 by r square equals to c1 capital R, this by capital R square is r omega. Now cancelling r from each side, we will be getting divide by these terms, we will have now solving after our boundary condition, we will be getting our C1 equal to 0 and C2 equal to omega r cube. And after that, we will be putting all these things in our V file. V file will be get omega r upon r square by small r, this will be bracket actually, multiplied by sin theta. So this will our velocity profile in phi direction. Now as we have to calculate the torque, we will be needing force multiplied by area, shear stress multiplied by area, which will give us force, and integrating that force we will be getting our torque. So and our torque equation will be integration of 0 to 2 pi, 0 to pi, our shear stress of r phi at r equal to capital R multiplied by r sin theta into r square sin theta d phi. So this will give us our torque. And after evaluating that integral, we will be getting putting our tau r phi equal to minus mu 1 by r sin theta del vr by del phi plus r into del by del r of v phi upon r. This will be our torque, and putting that into the integral, we will be having 0 to 2 pi, 0 to pi, 3 mu omega sin theta r sin theta r square sin theta d theta d phi. And evaluating our outer integral, we will be having 6 pi mu omega r cube 0 to pi sin cube theta d theta, and finally we will get 8 pi mu omega r cube as our torque. This will be our final torque. So our velocity profile is omega r by r of whole square into sin theta, and our torque profile will be 8 pi mu omega r cube. So this is our velocity profile, and this is our torque. This is torque required to rotate the sphere. Now why we are calculating this torque? Because different fluids having different viscosities. So any particular fluid, we have to change the viscosity of the fluid, so torque will be different. And also we will be having some different omega. The main condition of omega is the omega should be sufficiently small so that the flow is become laminar, and not the turbulent condition will be arrived. Along with we'll be having different radiuses of our sphere, like we'll be having small sphere, we'll be having larger sphere. So all these factors in putting in consideration, we'll be having our formula for distribution of torque. So will be needed this. Now here we are. After discussing the problem thoroughly, we should understand how problem is exactly there, and every corner cases, like every small information about the problem, we should able to answer. Now checking this thing with my friend, we have framed some small question and answer related to the problem. Like it will be very basic question that if you understand the problem, like you should listen to the problem and then you should able to answer the small question. So moving on to our first question, how does the torque on rotating sphere changes if the radius doubles?
The answer of this question is torque scales as r cube, so it increases. Suppose we are taking 8-fold example, it becomes 2 raised to 3 is equal to 8. It becomes it changes as r raised to 3 power. Second question, why does V phi decay as 1 by r square, not exponentially?
Now this was a very simple question. Answer to this question is as we have discussed in previous clips, we have shown that the velocity profile shows inverse square law. That means it was proportional to 1 by r square. So any exponential term is not there in the expression of velocity. So obviously it not decays exponentially, it decays 1 by r square. Now, my next question to you is what happens if the fluid is non Newtonian? Example like any ketchup, any honey, any oil.
For this question, if we are taking example as ketchup, the stress strain relation becomes non-linear. So we have to require new models for this. We require generalized Newtonian models. For example, we use in this case power law as we are taking the substance ketchup. We will use here power law.
Okay.
Question number four. Could this analysis apply to a rotating cylinder?
For rotating cylinder, I don't think this analysis could be applied. Like for sphere, we have r coordinate, theta coordinate, and we don't have phi coordinate there, right? We have z coordinate there. So this analysis is mainly based on the phi coordinate, and every equation which will be applied here is spherical equation, like Navier-Stokes equation in spherical coordinate. So this analysis, this same kind of analysis, couldn't be applied on the spherical coordinates, cylindrical coordinates. Sorry, but the basic approach of shell balance which will be applied in cylinder also. My next question is how would gravity affect this system?
Mm, Gravity is negligible for small sphere and it will be higher for larger sphere. So otherwise introduces buoyancy driven flow, example sedimentation case. So there is a negligible gravity for these small pairs.
Okay.
So next question is what's the role of the no slip condition here in this case? So let's answer.
Ensuring our v phi equal to r omega sin theta at r equal to capital R, creating viscous shear. So this was our no slip condition here. My next question to you is how does torque relate to energy dissipation in the problem?
Um, there is a relation, we will see relation power dissipated is equal to tz omega is equal to 8 pi mu omega square r cube. This is a relation to energy dissipation showing energy loss to the viscosity. So
Okay.
we are going to explain the next question. The question number 8 is what if the sphere oscillate instead of rotating steadily? What will be the answer?
Uh, if our sphere start to oscillate instead of rotating, that will be case of unsteady flow. Our problem is indicating the steady flow laminar condition. So oscillation does not come under this case, as oscillation will be there. So our problem become unsteady and variation of time, velocity variation with time will be seen. My next question to you is there a critical Rayleigh number for turbulence in the rotating flow?
Mm, S. Uh, there is a Taylor instability occurs at a Reynolds number which is greater than 41.3 for concentric rotating cylinders. So there is a Taylor instability for the Reynolds number greater than 41.3. So next
Okay.
question number 10 is how is this used in industrial mixers?
Uh, as we have discussed further, the similarity between rotating sphere as impeller generate shear thinning, like in non-Newtonian fluid by rotating blades. So our industrial application for this case is impellers only, as impeller also used for rotating purpose and mixing purpose only.